going to talk about the ideal gas law, which is formed by creating all of the simple gas laws. And there's another one we didn't learn about called Gay-Lussac's law. But these are the three we learned about. Let's see. Relationship between volume and pressure, volume and temperature, volume and amount of moles. And I'm not going to go through all the math about how that works out. If you're interested and want to know about that, you can ask me later. Bottom line, PV equals nRT, ideal gas law. Some people call it PIV-NERT. So PIV-NERT has pressure times volume is equal to amount of gas in moles times R times the temperature. R is a constant. R is the ideal gas constant for the ideal gas law, and the value of it will depend on what units you're using, but these are the units we're going to use. So if we use liters for volume, atmosphere for pressure, moles for amount, and Kelvin for temperature, then it has a value of 0.08206. Liters times atmospheres divided by moles Kelvin. And the units here tell you, get all of your other parameters to match up with these units, and then the equation will be good. This is showing the relationship between these different gas laws. What I want to show you is that just from PIV-NERT, you can get any equation that you need. Okay, so if I have PV is equal to nRT, okay, ideal gas law, and we'll say this is one set of conditions. R doesn't get a number because it's always the same. Under a different set of conditions, P2 times V2 is equal to N2 times R times T2. This is equal to this. If I divide this side by that, and I divide this side by this, which is equal to what I divided the other side by, then it's still equal. Okay? If it doesn't make sense to you, just, well, Mrs. K said, put ones on the first one and twos on the second one and divide one by the other. That's fairly simple to remember. Now what you're going to do is you're going to cross out anything that's not changing. So R doesn't change because it's a constant. So R doesn't change. So what if we were trying to get Avogadro's law? So we have a problem where we've got volume and amount of gas changing, but the pressure's constant and the temperature's constant. If the pressure is constant, that means that pressure 1 is equal to pressure 2. They're going to be the same number. We don't actually need to know what they are. They're going to cancel out. And if the temperature is constant, T1 equals T2, and those cancel out. So now we have V1 over V2 is equal to N1 over N2. You're like, that kind of looks like Avogadro's law. Well, if we rearrange it, we can swap the top on one side and the bottom on the other. It's kind of a short version of cross multiplying. Oops. There's Avogadro's law. Now, there's at least one question on the worksheet today that's going to require a simple gas law that wasn't given in the book. So we looked at volume and pressure, volume and pressure, volume and temperature, volume and N. We didn't look at like pressure and temperature or pressure and amount of gas. But you can do this to get whatever equation you need. Okay? So, ideal gas law. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire. So reading this problem, I mean, obviously we're talking about the ideal gas law, and it says ideal gas law at the top. But on an exam, they're not going to be labeled like that for you, right? How do you know what kind of a gas law, what equation to use? Well, the ideal gas law problems, we don't have things changing, right? All those other ones they were heating this to that, or adding, or something was changing. Here, nothing's changing. That's what clues me into it being an ideal gas law problem. We can also just take the same approach and make a table and see what we get. So let's try that. I'm going to pretend I don't recognize this is an ideal gas law problem, and I've got this number, and this number, and this number, and I'm trying to find pressure. So I'm just going to make a table and collect this information and go from there. So the first thing is 8.50 liters. Is that P, V, N, or T? That's V. We know because liter is a unit of volume. Next number is 0.552 moles, and that is N, amount of gas in moles. Next number, 305 Kelvin. What's that? That temperature. I ran out of numbers. I only have one row of numbers. When we did this before, we would end up with ones and twos, right? We'd have 4 boxes and one was blank. So that's what tells me this is the ideal gas law. Did we waste our time by making this table? No. I now have all of these things labeled. So it's all good. I'm just going to erase this part, because then it looks like I knew what I was doing to start with, right? Yeah, I meant to do it like that. So PV equals nRT. I'm trying to find the pressure. Thankfully, the ideal gas law does not have any fractions in it. So we can just set about rearranging. So if I divide by volume, the volumes cancel out here. So that tells me that the pressure of this gas is equal to N times R times T divided by V. What's R? It's not in the problem. You'll save yourself some time if you memorize it, but it will be given on an exam. R is equal to 0.08206 liters times atmospheres over moles times Kelvin. Yes, write out all those stupid units. Okay, so now we can plug the numbers in with their units. 0.552 moles times R, 0.08206 liters times atmospheres divided by moles times Kelvin times the temperature, 305 K, divided by the volume, 8.50 liters. I didn't talk about checking these units to see if they match up what's in here. We just kind of went ahead. Let's check now. So here I have moles, and those are going to cancel out. And I have liters and liters. Those are going to cancel out. I have kelvins and kelvins. And if the fraction within a fraction bothers you, I'd be happy to show you how that works. So I'm left with a unit of atmosphere, which is a unit of pressure, so that's nice. So I'm going to do this up here. Maybe I'll change the color so it doesn't run together. So 0.552 times 0.08206 times 305 divided by 8.5. 1.625. How many sig figs? 3. So there's 3. I'm going to write down 2 extras just because that's what I do. Atmospheres. So this is asking for 2 answers, the pressure in atmospheres and the pressure in PSI. So the pressure in atmospheres would be 1.63 atmospheres, right? 3 sig figs. To get PSI, I need to convert this. So I'm going to multiply PSI on top and atmospheres on the bottom, so the units cancel out. Converting pressure units, you can always do it in just one step. You can make a whole string of things if you want to, but it can be done in just one. So then I go to my table of pressure conversions. Don't go to Google. Hey, you're going to get weird numbers, and I'll see that they're weird numbers, and I'll question you about it. I mean, you can get the right answer still, but you don't have it on the exam, so just practice how it's going to be on the exam. So you look this up, and it says 14.7 PSI is equal to 1 atmosphere. So I take that pressure in atmospheres and I multiply by 14.7, and that's going to give me 23.893, again with 3 sig figs. So 23.9 PSI is the other answer. Any questions? Yes?
Will we get that, the PSI conversion on the exam?
I'll give that to you. Yeah. The only pressure conversion that I think you should memorize, and really just to save yourself a lot of time, is that an atmosphere is exactly the same as 760 torr or 760 millimeters of mercury. That one gets used a lot. And if you have to go look it up every single time, it just takes a lot of time. But the rest of them, I only remember it because I do this all the time. Otherwise, I wouldn't remember either. Any other questions? What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? Do we see anything changing? No. So this is not going to be Boyle's law or Charles' law. It's going to be the ideal gas law. So you can make a table if you want, or you can just pull out the numbers and label them. So here I've got moles of gas, and I've got millimeters of mercury, and I got 58 degrees Celsius. So 0.556 moles, 715 millimeters of mercury, 58 degrees Celsius. So these should correspond to P, V, N, or T. Right? So moles of gas, that's going to be N. The pressure is P, and this is a temperature. And it even told us that. Pressure of, temperature of, what's the volume? PV equals nRT. We're trying to find the volume. So if we divide by the pressure, we get volume is equal to nRT divided by the pressure. Let's write down the ideal gas constant here as well, 0.08206. Liters times atmospheres over moles times Kelvin. Are these the right units to use? No. Moles is fine, but millimeters of mercury isn't going to work, and degrees Celsius isn't going to work. Let's convert them before we stick them in. So millimeters of mercury to atmospheres. One atmosphere is 760 millimeters of mercury. 0.94029 atmospheres. Remember, we don't want to round the numbers when we're going to use them in more calculations. Here's our temperature. So we're going to add 273. I'm going to go ahead and do the 0.15 because this is a big old mess anyway. 273.15 plus 58 is 331.15 Kelvin. We're adding, right? So this was in the ones place, so this one is in the ones place for the last sig fig. So volume is equal to amount in moles, 0.556 moles, times R, darn it, there, that'll work. Temperature, 331.15 Kelvin. And we're dividing all of that by the pressure in atmospheres. Atmospheres cancel atmospheres, moles cancel moles, kelvins cancel kelvins. 0.556 times 0.08206 times 331.15 divided by 0.94079 equals 16.0597, and that is liters. I guess I can fit that in liters. And this again would have three significant figures. 16.1 liters is the volume. Any questions? There's like an infinite number of problems that could be asked with the gas laws, because you've got all these different numbers and you can change the units and you can make up all kinds of crazy stories. I haven't seen one with a train going 55 miles an hour yet, but I'm sure you could work that in there somehow. 16.1. Okay, here's another one. Determine the pressure in millimeters of mercury of a 0.133 gram sample of helium gas in a 648 milliliter container at 32 degrees Celsius. Deep sigh, I get you. I did all these problems yesterday. And last semester, and the semester before. Things were given, things we're looking for. So I've got 0.133 grams. I've got 648 milliliters. I've got 32 degrees Celsius. Well, that's a temperature. This is the volume. And that's a mass. PV, N, or T. N is amount of gas in moles. So we can make this into amount in moles. That's an amount in grams. It's helium, so we need to convert it to moles. Dividing by grams. Periodic table says 4.003. 0.133 divided by 4.003. 0.033225 moles. Is milliliter a good unit here?
No.
No, we want liters, right? So there's different ways you can do that conversion to liters. Some of you are good at doing it in your heads. Some of you are good at being consistently wrong doing it in your head. So people will tell me 648 milliliters is 648,000 liters. That's like saying an inch is 12 feet. You went the wrong way, right? So if you're one of those people that ends up getting this wrong, don't try to do it in your head. We can convert this really easily by just writing what milli means instead of the m. Milli means 10 to the minus 3. So we can just say, well, this is equal to 648 times 10 to the minus 3 liters. Not proper scientific notation. Calculator doesn't care. And I don't care because it's not your final answer. So that's the easy way to do it. Celsius doesn't work either. So convert that. .15 Kelvin. R 0.08206 liters, atmospheres per mole, Kelvin. PV equals nRT. And this time I'm looking for the pressure. Divide by volume. So the pressure is equal to nRT over V. 0.033225 moles, 0.08206 liter atmospheres per mole Kelvin. Temperature 305.15 Kelvin. Saved that one. Divided by the volume, 648 times 10 to the minus 3 liters. Moles cancel, liters cancel, Kelvins cancel. .03325 times 0.08206 times 305.15 divided by 648 EE minus 3. And that'll be atmospheres. Now that's a great answer, but it's not the correct answer yet. Wants millimeters of mercury. So we have to convert. One atmosphere, 760 millimeters of mercury. Any questions? This is 976. Anybody else do it in a calculator? Did you get 976.5? I think that's probably because I included the 0.15. That would make my final answer slightly bigger, so it rounded. Is that something we need to worry about? No. Because the difference between our answer and the book's answer is in the last significant figure, where there is uncertainty. And so, depending on, how you converted your temperature there, I say that I'm right because this is the better way to do it, but, you know, the book is the book.